how to how to generate such an ultrasound. And this problem actually is solved, and some parts of the problem is still under development. And the main effect here, which is used, it's effect-based, which is piezoelectricity. And piezoelectricity was discovered at the end of 19th century here in France by Curie brothers. And the effect is the following. When you compress or bend some solid materials, then on the opposite side of this material, there is electrical charge. And this is called piezoelectric effect. And also there is, the effect is reversible. For instance, if you apply voltage to the opposite sides of the material, then it starts to compress or to expand. This is so-called converse piezoelectric effect. And also in France in 1917, Paul Langevin, he proposed to use this approach to generate and to receive sound. And since then, actually, the effective way of generation ultrasound of frequencies very high, including megahertz frequency range, became possible. And if you think about what kind of materials, not all the materials, they have this property of being piezoelectric. There are some natural crystals in the nature, like tourmaline or quartz or lithium niobate, which actually are good piezoelectric materials. But the real progress here started when people actually succeeded to make artificial materials. And the most important of them is so-called piezoceramics. Piezoceramics, they are similar to usual ceramics, but they have these piezoelectric properties. And what is good, you can make those samples different shape, different size, so it's easy to make. And also it's cheap, relatively cheap. And so after they were discovered, most all of the modern sources start to use piezoceramics. And how the sources look like, they are shown here. And typically it's piezoceramic plate. Sometimes there are many of them. So you apply electric voltage to this plate, and through cable, everything is in some case. And now so in this sense it's simple. And now you apply voltage at the frequency you want, in this case megahertz, and the surface of the piezoceramic elements start to vibrate with the same frequency. And now if you apply this device to the medium, like tissue, you will have ultrasound propagating from this source. So it's quite simple and efficient. It's important to notice that piezoelectricity is not the only possibility to generate ultrasound which can be used in medicine. There are other actually physical principles which are also efficient. For instance, you can make a discharge in liquid, and then you have electrical spark, like a small explosion. Now you have a spherical wave which propagates from this spark, and you can direct it somehow to the medium. There is also so-called electromagnetic source, when you have a coil and a membrane, and when you apply a current, this membrane starts to move, and you have again generation of short pulse. There are even laser sources or ballistic sources, so different approaches. And they're used in medicine, not only piezoelectric sources. For instance, those pulse sources used in lithotripsy. This is procedure when short, intense ultrasonic pulses, they're used to fragment kidney stones. But not only pulse sources can be created by non-piezoelectric manner. There's also continuous wave sources, which are called capacitive micromachined ultrasonic transducers, CMUTs. And it's a kind of one of the examples when the technology can actually result in new principles of sound generation and reception, but they are still under development. And if we analyzed the situation now, the most important, cheapest, robust, and efficient way of generating ultrasound is using piezoceramics. So it's mostly all the transducers, as a rule, they are made from piezoceramics. Now we know how to generate ultrasound, and the next question is how to focus it. You know that I mentioned that to focus you need wavelength which is small compared to the size of the source. Imagine that we have this condition, and now what to do? And of course, the natural, like the first thing that came in mind is to use optical approaches. What we do in optics, we use lenses, we use mirrors, right? And the same can be done with ultrasound. For instance, lenses. They can be convex or concave or convex, depending on the speed of sound or speed of light, if it's for light, but we're discussing here ultrasound. If the speed of sound is lower or higher as compared to the speed of sound in the surrounding medium. And both cases actually can be realized. And so as a result of this going through the lens, the wave becomes focused and it can be used similar to optics. Another approach is this one. This is when you use curved mirrors, reflectors. For instance, if you have paraboloid and you use a collimated light, you send a collimated light to this paraboloid after reflection, all the rays, they go to the same point. That means that you have focusing. So this approach is also can be used, and it is used actually in some applications. But these optical waves of focusing, they're not actually as good as the other methods that I will describe right now. Why they're not good? For instance, because the lenses, they can be quite absorptive. So you have energy loss. Also, some energy loss happens because of the reflection from the lens interfaces with the medium. The same for reflectors. They are sometimes too big and not easy to use. And with ultrasound, actually, there's other principles. And there are two main, maybe, ideas here. And one is based on the fact that you can make the piezoceramic, for instance, plate not flat, but curved. Imagine that you have this kind of curved, it's here, shape. And if you excite now this piezoceramic plate, it will start to vibrate. And of course, it will emit the wave which are actually should propagate to this center of curvature. Indeed, if you look at this, how the elementary waves from the surface elements would propagate, you can see that they converge to the center of curvature. And now you have focusing. You have high intensity at the center of curvature. Now, if we don't have this curved transducer, we have a flat transducer. Can you do that the same? You may say that you can do it using lens, but we already decided that lens introduce some losses. There's another idea. Imagine that you, instead of having one plate, you divide this plate by smaller elements. And because piezoelectricity means that you can apply different voltage to different elements, now you can excite them actually independently. And for instance, imagine that you excite first the elements which are close to the edge. And then next, the elements which are farther from the end, from the edge. And then even closer to the center of the transducer. What you will see, you will expect that you will have focusing as well. Indeed, look. So the wave propagates. And now, again, the convergence is to the same point which you actually set beforehand. So to repeat, the idea is the following of non-optical wave of focusing. You have either the curved transducer or you have the multi-element array when there are many elements on the source. Those actually sources, I forgot to mention that, they are called arrays, and this terminology came from radio waves, where similar principles were first proposed. So now if you have multi-element array, you can excite it in the way that after excitation, again you have the wavefront which is curved, which is spherical, and now you have focused wave. Again, no lenses, no mirrors. It's quite a beautiful idea, and the second idea actually with the multi-element array, it's quite elegant and the most powerful. The price for this efficiency is that you need to have not a single element, but you need to have many elements and drive them independently. But nowadays it's not a problem. The ultrasound technology is developed well enough so that we have these sources. And here's an example how the source look like. First it was designed. Usually it's many elements, like hundreds, sometimes even 1,000 elements, which lie on the surface. It can be flat or slightly curved. And then each element is actually excited by independent wire, independent cable, so that you have control for all elements independently. And here, actually, at the bottom, you can see the fabricated array. This was designed. This was fabrication. You can see that there are cables behind it. And also, one maybe technical thing that I should mention: when you drive the piezoelectric sources, you need to be sure that the electrical source of each element sends the energy to the element in an efficient way. People say that they should be matched, electrically matched. For that, there is special circuit. This is a matching network, and there's an example how it looks like. You see many elements, and this is just to make it more efficient. So it works. And there are already many arrays, or many types of arrays designed, and some of them are in clinics, in the clinical machines. And at the left here you can see the first, maybe the old design. It's 64 elements transducer, and now they are transducers, multi-element arrays with the number of elements like 256 or even more than 1,000 elements. And so it works, and it's efficient, and it's really can be done. And what can be done actually with this kind of multi-element array? Imagine that you have this array, which is shown here, and there are many elements. And now you, as I mentioned, by sending the proper phase or proper delay to the elements, you can create focused wave to some point which you want to focus at. But if you change the phase shift, we can focus to another point or to another point. But so then we can shift this point constantly, and this shift is called sometimes electronic steering. Electronic because it is not shifted mechanically, it's shifted because of the electronic circuits which drive the phase. And what can be done, look, so this hotspot, which is where the wave converge, it's moving. And this approach is quite, without moving the source. And it's quite useful, especially when, for instance, if you want to treat some big volume of tissue and the focal spot is tiny, so then you move this focal spot in this region, and now you can treat the bigger volume of tissue. So it's very elegant and efficient approach. And I show this slide not for you to read it and to understand it, just to mention that not only this hand-waving explanations work in this case, everything is based on this quite strict mathematics, because ultrasound is wave, so those waves are described by mathematical equations. Usually they are called wave equations. They are differential equations, and they can be solved, sometimes numerically. And here's an example of what the theory predicts in case of ultrasound wave. You have the source on the top, and now it emits ultrasound wave, and it propagates down, and as you see, it's converged in the focal spot. And this is pressure, actually, distribution in time and in space. But if you want to feel how much energy is transported, then people use usually the characteristic which is called intensity. Intensity, this is how much energy passes through the unit area in unit time. It means that how efficient you transport the energy. And the image on the right is intensity distribution. You see that indeed, close to the focus, there is high intensity region. But what is also important to say that it's not only one point. It's the extended actual region. It has a shape like of extended ellipsoid. In case of applications in therapy, actually the size of this region is about the size of the grain of rice. Sometimes this analogy is used, so it's a really tiny millimeter size spot. And all the energy which is emitted by the large surface of transducer is actually collapsed to this small region. And you can imagine how much amplification you would have, and the pressure field is quite intense there. That is why it is called high intensity focus ultrasound. Actually, mathematically, these dimensions of the focal region and also the intensity, the focusing gain, all this can be predicted. And in the simplified case, you can see here that actually the sizes of this region the length and the width, they are on the order of the wavelength, not about the same as wavelength. There is also a factor which is related to the angle of convergence. So now you can exactly predict the size of this focal region. And it's as when you increase the frequency or you decrease the wavelength, now the region becomes smaller. And then you have more concentration of energy and better focusing. Can we see this focused wave? I said that the only wave that we can see, maybe it's light wave or waves on the surface of water. Sound and ultrasound, they are invisible, but in fact they are visible. They can be visible, so they can be visualized if we use so-called shadowgraphy. So when you send light through the field of ultrasound or sound, there is a shadow. And this is approach, sometimes it's called schlieren, can be used. For instance, here you have an example of the shock wave which propagates from the gunshot in air. Similar things can be used for to visualize ultrasound. And here's the example of how it can be done. For instance, when you have a source on the top, now if you send a pulse light, you can see that after excitation, there is a propagation of waves. There is periodicity, which is wavelength period, and then everything converges to the focus. If you, instead of using pulse light, you use continuous light, then you can see intensity distribution. And this movie, this one, shows how intensity distribution looks like when you increase the power of the source. So initially it's weak power and then higher, higher, higher. And you can see the structure, special structure of the beam. It's indeed converging, and the maximum intensity happens at the focal spot, and it can be seen. So we can generate ultrasound, we can focus it, and now the next question is what can be done with this high-intensity ultrasound. It's very intense, and it's so intense that it can create changes in the medium. And this is actually the idea of using ultrasound to make changes in tissue. What kind of effect? I'll mention several of them. One effect which is quite interesting and quite easy to see is so-called acoustic fountain. If you take a source and now you direct it, you place it in water and you direct it to the water surface so that the focus is on the surface of water, and you turn on the power. Starting from some power, you'll have a jet which goes up from the surface, and this is so-called acoustic fountain. And it's not only a jet, actually. There's also a steam around the jet, the effect which is usually called attenuation. And this is just the result of focused ultrasound. You can imagine that what can be done in materials like not liquid, for instance, in tissue, similar effect may happen. And showing the acoustic fountain, it's a usual thing that we use in the lab to attract students to show how intense is the ultrasound. And this is the example how it looks like. For instance, you have a water bath and now the source, which is small, and you see this jet. It's quite impressive demonstration of the intense ultrasound capabilities. What else can be done? For instance, if you send ultrasound inside the medium, and as I mentioned, it's not only energy, but also it's pressure. It means that you have compression, expansion, compression, expansion. So when you have tension at some level, starting from some amplitude, the medium cannot sustain this stress, and then cavity appears. Or in case of liquid or tissue, it's bubbles. And this effect of generating bubbles by intense ultrasound is called acoustic cavitation. And this cavitation results in appearance of bubbles which grow and collapse and can also participate in the damage of tissue. And this movie actually shows how it happens. You see, these white regions, they are bubbles. But you also can see that the bubbles and small particles like dust particles, they also move. This is another effect of intense ultrasound. This is so-called acoustic streaming. This is hydrodynamic flow which is created by the intense ultrasound. So cavitation, hydrodynamic flow, both happen. What else? The next thing is related to the fact that ultrasound actually transport energy. and then it is released at the focal point, and now you can hit the medium. This is maybe the main, so far, the main effect that is used for HIFU therapy. So, here you can see an example when ultrasound was actually focused inside a transparent gel, which is tissue-mimicking gel. Sometimes in the lab we use this kind of materials, and you can see that far from the source, in the focal region, you have these changes and damage. And this is the same similar things happen in tissue. We cannot see through tissue, but we can prove that the same effect happened there. The next maybe subject that you cannot avoid when you discuss ultrasound is how it propagates. Actually, if you take a wave, any wave, when it propagates in the medium, it not only propagates with some speed, but also it loses its energy while propagating because of absorption and scattering. And this effect of decay of energy or decay of amplitude is called attenuation. And for plane wave, for instance, the attenuation happens in the way like the amplitude decays exponentially. And if you look at this scale, and this scale actually shows how long the ultrasound propagates, or any wave, not only ultrasound. And this decay actually is explained by this coefficient alpha, which is called attenuation coefficient. The higher is the alpha, the quicker is the decay. And this coefficient can be measured, and for different type of tissue, it was measured, it is known. And for instance, it depends on frequency, it depends on type of tissue. For instance, in skin, it's maybe one of the highest for soft tissue. But if you compare skin with kidney, in kidney it's like 10 times less. But in average, the ultrasound propagates quite long. It's about 100 wavelengths. And it's actually a good thing about ultrasound. The light, as you know, cannot penetrate inside the body. It can, but not that deep. For ultrasound waves, our body is almost transparent. But not exactly transparent. It's partly attenuates, and that is why we can create the effects. So what happens when now we send this ultrasound inside the tissue and we achieve high intensity at the focal spot and the focal region? There are several effects, and depending on, there are actually many parameters of ultrasound. It is amplitude, frequency, if it's pulse duration, pulse repetition, the structure of the field, and many things. And depending on the parameters, we can create different changes in tissue. For instance, here you can see this an example when you hit the tissue and you create so-called purely thermal lesion, when you just hit the tissue and it is destroyed because of the overheating. If you hit more intensively, you can actually create this effect in combination with some vapor bubbles boiling, and then you have different lesion. If the intensity of ultrasound is even higher, or in some regimes you can create paste, or sometimes even liquid. So the effect can be different, and the mechanisms are sometimes thermal, sometimes mechanical. And by choosing the proper parameters of ultrasound, you can create this kind of changes. And this is the basis for all the therapeutic use of focus ultrasound.